In this video, we present our work, RankMixup, ranking-based mix-up training for network calibration, from Yonsei University. While deep neural networks achieve impressive performance, they often suffer from overconfidence when trained with softmax cross-entropy and one-hot encoded labels, leading to inaccurate probability estimates. To address this issue, network calibration strives to precisely assess the confidence levels of deep neural networks. This is crucial when deploying these networks in practical real-world applications. To enhance the reliability of DNNs, train time calibration methods add an extra regularization term during training. Several studies have examined the impact of regularization techniques on network calibration, demonstrating their effectiveness. However, recent works have uncovered limitations in label smoothing and focal loss regarding network calibration and proposed calibration-aware versions of them. In contrast, there is relatively limited exploration of integrating the Mixup technique into network calibration. Mixup assumes that target labels for the vicinal set should be interpolated with the same mixing coefficient applied to input samples. However, the interpolated labels of augmented samples in the vicinal set may not always accurately model the actual distribution of label mixtures in those samples. Prior Mixup-based calibration methods have typically used label mixtures to soften output probabilities. However, training networks with such uncertain labels degrades the calibration performance. In this work, we introduce RankMixup, a Mixup-based approach to network calibration that tackles the issue of directly using label mixtures for calibration. Instead, we propose leveraging ordinal ranking relationships among confidences from original and augmented samples as well as among confidences from multiple augmented samples as supervisory signals. We also introduce to-loss functions aimed at aligning confidences and mixing coefficients to preserve these relationships. RankMixup utilizes to ordinal ranking relationships. The ordinal ranking holds for the relationship that confidence levels of easy-to-classify samples should be higher than the ones for hard samples. Accordingly, we initially assume that confidence levels of raw samples should surpass those of the augmented samples during the mixing process. We then extend our framework to leverage multiple Mixup augmented samples. As the mixing ratio decreases, augmented samples become progressively more challenging to classify. Similar to the single-case scenario, we expect that samples augmented with larger mixing coefficients will exhibit higher confidence levels compared to those with smaller coefficients. We introduce the Mixup-based ranking loss, MRL, that facilitates the ordinal relationship in equation 1. It encourages confidences of augmented samples to be lower than those of raw samples by a margin. Unlike vanilla Mixup, which persistently penalizes augmented sample confidences, MRL penalizes confidences only when discrepancies fall below the margin. MRL is not sufficient to model the relationship in equation 2, where the comparison involves more than one augmented sample. To address this, we introduce MNDCG, a Mixup-based NDCG, loss. It enables the preservation of ordinal ranking relationships among multiple confidence values. It draws inspiration from the normalized discounted cumulative gain, NDCG, metric used in information retrieval to evaluate ranking quality. NDCG quantifies the alignment between retrieved results and the ground truth ranking order by normalizing a discounted cumulative gain with an ideal gain. DCG accumulates relevance scores weighted by rank, and IDCG is computed similarly, but with ground truth scores. In the context of MNDCG, we treat prediction confidences as relevance scores and mixing coefficients as ground truth scores, allowing multiple confidences to conform to the relationship described in equation 2. MNDCG is minimized when the ranking orders of the confidences and mixing coefficients are aligned to each other after sorting in descending order. This encourages the network to maintain the ordinal ranking relationship among confidences. For further information, please refer to our paper. To train our model, we use a CE loss for classification, together with either MRL or MNDCG for network calibration. As supervisory signals, we exploit one-hot encoded labels for classification and ordinal ranking relationships for network calibration. We compare our method with state-of-the-art calibration approaches. Our models outperform other Mixup-based methods using label mixtures as supervision, demonstrating the effectiveness of leveraging ordinal ranking relationships for confidence calibration. Additionally, our model achieves the best performance in terms of both ECE and AECE on the tiny ImageNet dataset. We present additional experiments to demonstrate the robustness of our framework under distributional shifts and with imbalanced datasets. Our models trained with MNDCG excel in out-of-distribution detection, outperforming other calibration methods. Our models also exhibit improved calibration on long-tail datasets, despite not being explicitly designed for them. We also analyze the impact of the Mixup coefficient on our method. Our findings indicate that our models achieve optimal performance with alpha values of 2 for CIFAR 10 and 1 for tiny ImageNet, respectively. This suggests that employing diverse Mixup coefficients drawn from such distributions enhances calibration performance by enabling more diverse sample augmentation. For more information, please see our paper. Thank you for listening.